All right. So this is why you guys are here. This is why everybody takes chemistry, right? You all take a challenging course because you want to see things burn up or blow up.
Is today that day?
So you want to see like fire. Give me some fire. I'm sorry, what? Oh yes. Can you be quiet? I'm going to do that.
See, actually, that is where I am. Turn a little bit more this way. There we go.
Okay. So this is the last unit in the semester, and we're going to start it this semester, and then we're going to finish it next semester. It would be great if we could finish it all in quarter one or quarter two, but we can't. Okay, so, ladies and gentlemen, it's important. This is totally cool. This is my new torch. I got this summer. It's a creme brulee torch. So if you want to play with fire, become a chef. It's important when you're doing activities because if you don't have a plan, then you're.
Wait, do it again.
How can you do it again? It's gone.
If you don't have a plan, then your future is not going to be good either. So it's important to have a plan.
Wide interpretation of how easily life can go wrong.
Exactly. If you don't have a plan, your future is gone. Just like that. Just your plan goes away, then so does your future.
Yeah. Where does
All right.
it go?
So you're breathing it in right now. You're breathing in the carbon dioxide that is produced in the combustion and the water vapor that is produced in combustion. So, yeah, just a little bit of a preview. That is one of the 5 reaction types we're looking at. And that is called a combustion reaction. In a combustion reaction, fuel reacts with oxygen to produce CO2 and H2O. So these are both greenhouse gases, the CO2 and H2O. So I just killed a little bit of our ability to live on the planet. Yeah. And I'm going to do it again. Yeah. I'm doing it right now. So plant some trees. If you want to live on this planet, or you want your kids to live on this planet, plant some trees. Yeah, hashtag Team Trees. All right, so today we're going to talk about chemical reactions, and we're going to do a bunch of them. So you're basically learning primarily 2 things. You are learning the 5 basic reaction types, and you're going to learn how to balance reactions. A balanced reaction is what happens when you have the same number of atoms on one side of the reaction and the same number on the other side of the reaction. No mass is lost. And in fact, that is Dalton's law of conservation of mass. It's so simple, we don't even give it a lot of time. We just say mass is neither created nor destroyed in a chemical reaction. It's just rearranged. So the atoms are neither created nor destroyed, they're just rearranged. That's a chemical reaction. Crossword? Yeah. Yep, okay. Now in a nuclear equation, we learned back in September, in a nuclear equation, yeah, you can make mass, you get rid of mass, you can turn it into energy, you can turn energy into mass. But in a chemical reaction, whatever mass you have before the reaction, you have after the reaction. In fact, if you were to somehow capture all the carbon dioxide and all of the water that came off, and you weighed it, it would weigh the same as that tiny piece of paper. Kind of cool, huh? Okay, so I set it down. There, stop sitting in the wrong place. Okay, so again, a reaction, a balanced chemical reaction works just like a balanced numerical equation. Just like 1 + 2 = 3, there's 3 on this side and 3 on this side. A balanced chemical equation exists when you have the same stuff on the left as on the right. Okay? 2 words of lingo to learn: solution and precipitate. A solution is just things dissolved in water. Okay? A solution is just stuff dissolved in water. A precipitate is a solid that has fallen out of reaction. You're going to see those a little bit later, probably tomorrow, depending on how much we get done today. So a solution is a water mixture. It's things dissolved in water. And a precipitate is something that is formed and falls out of the reaction. we doing so far? All right. Take a wild guess what we call the things that get reacted. Reactants. And guess what we call the things that get produced? Products. Now you guys are like, I got this, okay? And that arrow is called yields. That arrow is red, yields. So reactants react to yield products. So the reactants react, the products get produced, reactants yield products. Simple. Now, luckily, we read from left to right, and we also do chemical reactions from left to right. How convenient. Okay. Give me a thumbs up if this makes sense to you. Wave your hand around if you want to talk about it some more. Rock on. Okay. So, some symbols and notation. There's some symbols and notation that give you a little bit more information about the chemicals you're working with. Okay. If you see a little S written after a chemical, it's a solid. You see a little S written after a chemical, it's a solid. One of the things I'm going to do in this a little bit is I'm going to take solid magnesium and I'm going to react it with something. Not powdered magnesium. You have to buy that at the Indian reservations up on the 15th. If you see an L after something, it means it is a liquid. So I will also be playing with some liquids. One of the liquids I'm going to use is CH3OH, which is methanol. Yes?
When I was looking that up, I thought it was an I, and I spent 30 minutes thinking it was an I. I spent 30 minutes figuring out that question on the cross.
Your devotion is inspiring. 30 minutes. If you see a G after it, it means a gas. One of the most common gases we're going to react is oxygen gas. O2G. And one of the most important pieces of notation you have to know is AQ. AQ stands for aqueous. If you see an AQ after something, it means you're not seeing the solid chemical, you are seeing it dissolved into its ions. Let me show you the difference. NaCl solid. That you can put on your French fries.
That's just salt, right?
That's just salt. Okay?
Oh my god.
Now, however, if you see NaCl aqueous, this you cannot put on your French fries. This is a solution of water that contains the ions Na plus and Cl minus. Okay? So if you see an S after it, that means that's powder you can hold. If you see an AQ, it means it exists as ions in solution. Fun fact, this has no taste. This does. You can't taste salt until the ions disassociate and end up in the water in your saliva.
Oh.
Yeah, you can't taste this. This you can taste. Yes. You can't taste it. But I put it on my tongue. Here's a fun experiment. Dry your tongue out like what? And you'll hate that. Okay, sometimes these are a couple of old notations that sometimes you see. I haven't seen them in a long time, but every now and then you pop up on the internet and there's a tutorial that uses this. A downward arrow means a precipitate has formed. It's just a solid that has fallen out of the reaction. And an upward arrow means a gas that has bubbled out of the reaction. Again, really old notation, haven't seen them in a long time. What we usually do instead is we just slap an S at the end of the product, or slap a G at the end of the product. But should you see those arrows, that's what it means. A downward arrow means a precipitate has fallen out of the reaction, which I will show you tomorrow. And an upward arrow means a gas has been evolved out of the reaction, which I will show you maybe tomorrow, maybe today, depending how much time we get done today. And then sometimes you see things put over the yield sign. Sometimes you see the word catalyst put over the yield sign. Sometimes you see the word heat put over the yield sign. Sometimes you put a triangle over the yield sign, which also means heat. And sometimes you see a temperature put over the yield sign, meaning the reaction was carried out at a specific temperature. So those are just special reaction conditions that exist to basically tell the audience, this is what I did with the reaction. All right. If this stuff makes sense to you, give me a thumbs up. If you want to talk about it some more, wave your hand around. All right. Recall. Hammering it into you, because it's important. How many times have you heard about diatomic molecules? Someone raise their hand and tell me about a diatomic molecule. What's a diatomic molecule?
It's a molecule that can't actually exist by itself. It doesn't have another atom attached to it. So, like boron.
Not like boron, but bromine. Yeah. So yeah, exactly right. Thank you. So Matt said it's an atom that cannot exist by itself. It has to be bound to something else, and if it can't find anything else, it's going to bound to itself, like bromine. You're never just going to see a Br just chilling out there.
No.
You know, you can have a Br minus, so you can have a bromine minus chilling out in solution, but you're never just going to have a bromine by itself. It's going to have to bind to another bromine and make Br2. So that's the Br in Brinkelhoff. So again, those are our Brinkelhoffs. So if I was to take high voltage, and you can actually do this at home, take your car battery and get jumper cables, connect with the car battery, and stick the jumper cables in your fish tank. And what you're going to see is little bubbles are going to form around the jumper cables. Bubble, 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 bubble.
I don't think that bubble makes that noise.
No, and
Look at your phone. Now look at the screen. Now look at your phone. Now look at the screen. Now keep looking at the screen. Don't look at your phone. So if you were to do that, what you'd see is H2O is going to break down. Water breaks down into hydrogen and oxygen. Is this the proper way we should show it?
no.
No. How would you show it instead?
You need to flip it. Is it going to kill my fish?
Yes. It's going to look like this.
Oh.
Yeah, your fish are not going to enjoy the experience. But it's all for science, right? You're going to be like, whoa, look at him twitch. And if you don't have fish, then you can use or a glass bowl. So this is why you should never name your fish. You might have to electrocute them. So this is how we would show the electrolysis of water. So 2H2O becomes 2H2 plus O2. Now you'll notice there's some numbers that weren't there before. These are called subscripts. These big numbers are called coefficients. Subscripts, coefficients. Big number, subscript, literally means below writing. Coefficient, I don't know why they called it coefficient.
Wait, can you?
So the big numbers are coefficients and the little numbers are subscripts. When you balance, listen carefully. When you balance, you do not change subscripts once you have valid chemicals. O is not a valid chemical. H is not a valid chemical. H2 and O2 are valid chemicals. But once you have valid chemicals and you need to balance it, you only use subscripts.
So
Does this idea
subscripts
make
are the
sense?
number in front?
Yeah, you only add big numbers in front. You never change subscripts. Once your chemicals are valid, in most of the cases, it's going to be given to you. There's like this chemical plus this chemical becomes this chemical. So the chemicals will already be done. But when you're balancing, you only change subscripts. You never change coefficients. Okay, give me a thumbs up if you got that. Wave your hand around if you want to talk about it some more. Moving right along. Okay, so a reaction can release energy or produce energy. Most of the reactions that we're familiar with produce energy, but not all. Some reactions actually have to take energy in to keep going. Those reactions that release energy are called exothermic. Literally mean exit energy or outward energy. So a reaction that releases energy is called exothermic.
Yeah. What episode of Teletubbies was that? I might wanna watch
That was episode 1.
that is definitely
Welcome
not
to
episode one.
Teletubbies. This is Teletubbies, Robert Oppenheimer.
Yeah.
Teletubbies go to the bikini atoll. If a reaction absorbs energy, we call it endothermic.
Yeah.
Literally means inward energy. So again, we are usually familiar with exothermic reactions because these are things that release heat. You know, your phone warms up. But there's a very popular endothermic reaction that you're probably going to be doing a lot in the next couple of weeks, or your parents will be doing a lot in a couple of weeks. And then you put sprinkles on them. Baking. Baking is a very important endothermic reaction. Try to make cookies without an oven. They're going to be gross. There's this really valuable reaction that I'm going to show you a video of it later called the Maillard reaction. And the Maillard reaction is what gives cookies that golden brown flakiness that we all enjoy.
That's so good.
Yeah. So that reaction is an endothermic process. It needs to take in energy to happen. If you make your cookie dough, put them on the tray, and slide them into the oven, you're like, all right. And you come back after school, and you're like, they didn't make any cookies, or these cookies are gross. They're all gooey. You need heat to get that reaction to get going. Now, even exothermic processes, all processes, even exothermic ones, have what's called an energy barrier. An energy barrier is the energy required to get the reaction going. All reactions have it. Some reactions, the energy barrier is very small. Like, to get my butane going, all I need is a tiny spark. And it goes. Okay. Tiny spark, and it goes. Sometimes, if the spark doesn't go, nothing. There's gas coming out, but if the spark is not good enough, if I pull the trigger really slowly, sometimes it doesn't go, and there we are. Okay, the first time it didn't go. Now it's going every time. And then when I need it to go, it won't go.
Wait.
Power of positive thinking. It's going to go every time. Oh, see, it didn't go. Okay. So this is the energy barrier. This is called a reaction coordinate. Questions?
Wait, so the energy barrier, like in combustion reaction, when we wrote the fuel plus O2, is the fuel the energy barrier?
No. The fuel is a reactant. The energy barrier is the energy required to get the reaction to happen. So all reactions, even very exothermic ones, have an energy barrier. Sometimes that energy barrier is really big, sometimes that energy barrier is very small, but all of them have it. And the energy required to overcome the energy barrier is called the activation energy. That's the energy required to overcome the energy barrier, the activation energy. Made in the USA by Diamond. Cool. Matches and almonds, one of the few things that are still made in the USA. In California. Okay, so you've seen one of these, right? Little wooden stick with a little red goop on the end.
Yeah.
Yeah. You know how to make it go, right?
Yes.
How do you make it go? By striking it on the box, right?
Is that not?
So if you took your finger and you went on the box, my finger's getting a little warm because of friction, right? So that's how matches work. They need a little bit of friction to get going. That little red thing, it's obviously an exothermic reaction, but it needs a little bit of energy to get going. And then the consumption of the wood, the burning of the wood, is also exothermic.
Wait, I have a question.
Yes?
So the energy barrier is like a measurement, and the activation is it?
Yes, exactly right. The energy barrier is a value it must overcome, and the activation energy is the amount of energy it takes to satisfy the energy barrier. Okay. So any other questions?
Which is like the upward slope?
Yeah. So it's the difference between this point and this point. This is the energy barrier, and that number right there, from 20 to 100, that number, 80 units, is the activation energy.
Shocks you.
So if this is 20 and this is 100, the activation energy is 80 units of energy. All right, so rules for balancing chemical equations. I always like think we're gonna get a whole bunch done in the first day. Never do. But anyway. So this is a chemical. It has two subscripts. Rules for balancing chemical equations: never change subscripts. You can't do it. Don't do it. Don't even try. Don't do it. Okay. Next, if you find yourself with polyatomic ions, please balance those first. And understand that polyatomics do not break up in this class. Okay? I am going to give you reactions and ask you to do reactions where polyatomics do not break up. So please realize the polyatomic stays a block. The SO4 on the reactant side will stay the SO4 on the product side. It's not going to break up into other things. It's just going to be easier that way. Next, save single elements for last. This is not really a rule, but it's basically a really good technique. Save single elements for last, and you'll see why as we do a lot of practice with balancing. And lastly, this is also not a rule, it's a technique. If you find yourself with some odd numbers, balancing even numbers is a lot easier. So if you find yourself with a lot of odd numbers and you're confused, you're like, I can't get it, then make the odd numbers even numbers. So if you have like a 1 and a 3 and a 4 and an 8, turn that into a 2 and a 6 and an 8 and a 16. Okay? It just tends to make it easier. Not a rule, just a handy technique. All right, so let's do a really simple balancing. So this is the opposite of a reaction you saw earlier. Is this balanced the way it is? No, because there's two. How many hydrogens on this side?
Two.
How many hydrogens on this side? Two. How many oxygens on this side? Two. How many oxygens on this side? One. Not a balanced chemical reaction. Now, if we put these numbers in, we put these coefficients in, now it is balanced. How many hydrogens here? Four. 2 times 2 is usually 4. And how many hydrogens on this side? 4. 2 times 2 is usually 4.